Okay, so we're talking about section 14.3, which is finite fields. Okay, so finite fields. So first off, a field F has characteristic P for some prime P. So so a finite field F has characteristic P for some prime P. So it is a finite dimensional vector space over Fp. Right? It doesn't have characteristic 0 because if it did have characteristic 0, it would not be a finite field. It would be an infinite field. So it's a finite field, and it has to have characteristic P for some prime P. And then, therefore, its prime subfield is Fp, right? The field of P elements. What's generated by 1? It's just the first P numbers. And then you get back to 0, right? So this is a finite dimensional vector space over its prime subfield. So it has a degree. Let's call it n. And therefore, the cardinality of this finite field is p to the n for some n, which is the dimension of the vector space f over fp. Since the multiplicative group f star has order p to the n minus 1, it's just this minus 1 for the 0 element of fp. We have that alpha to the p to the n minus 1 is equal to 1 for every alpha in the multiplicative group. Right, so this is a group, first of all, and therefore, if you raise any element of the group to the order of the group, then you're going to get the identity element. Right. So alpha to the p to the n minus alpha equals 0. You just multiply both sides of this equation by alpha and bring the 1 alpha to the other side. So you get alpha to the p to the n minus alpha equals 0 for every alpha in F. Notice now that this equation holds even for when alpha is equal to 0. It's not in the multiplicative subfield, the subgroup, but 0 to the p to the n minus 0 is still 0. So this equation holds for every alpha in the field. Therefore, F is contained in the splitting field of the polynomial x to the p to the n minus x. Right, we just showed that every element of this field is a root of this polynomial x to the p to the n minus x. Since both have the same order, right? So what is the order of the splitting field of this polynomial? You have p to the n roots of this polynomial, and it's a separable polynomial. So this polynomial has p to the n roots, but this field has p to the n elements, and every element is a root. And by cardinality reason, every root is an element. So this finite field is the unique field of order p to the n. We just showed any arbitrary finite field of order p to the n has to be the splitting field of this polynomial x to the p to the n minus x over the ground field fp. So we just proved that every finite field of characteristic p is the splitting field of x to the p to the n minus x, where n is the degree of this finite field over fp.
Okay, I have a question.
Okay.
When you say the splitting field of the polynomial x to the p to the n minus x,
Yeah.
like over what field are we taking the splitting? Because like you need a base field, right, to have a
Yeah.
splitting field?
The base field is this finite field of order p.
Okay. Okay.
Yeah. So this polynomial has coefficients in this field because the coefficients are just 1, and 1 is in any field. So you can interpret this polynomial as a polynomial with coefficients in fp. And it has p to the n roots because any polynomial, any irreducible polynomial with coefficients in a finite field is separable. Okay. Now, notation, write f sub p to the n to denote the unique finite field of order p to the n. And this is kind of cool, a thing about finite fields. Once you specify the order of the field, you know exactly what the field is because there's only a unique field of that exact order. Next thing, the Galois group of Fpn over Fp is cyclic of order n and generated by the Frobenius automorphism. First of all, why is the finite field of order p to the n Galois over Fp, its prime subfield? Hold on. Okay, I'm back. So why is this Galois over Fp to the n? Well, we just showed that Fp to the n is the splitting field of a separable polynomial over Fp. So therefore we know it's Galois. We proved that the splitting field, we proved essentially that Galois field extensions are splitting fields. So this is a Galois extension. And now what's the Galois group? Natural question, right? So we know that the degree of this extension is n, right? Yes. Now, this means that the order of the Galois group also has to be n, because the order of the Galois group is the order of the extension. So the Galois group is some finite group of order n. Now, what exactly is it? Well, we know one element of the Galois group, it's called the Frobenius automorphism. We know that this is an automorphism. Well, why is it an automorphism? Because it's an automorphism. Let the ice cream truck pass. Yeah. Okay. So why is this an automorphism? It's an automorphism because we're in a finite field of characteristic P. Right. Okay. What does this automorphism do? It takes an element of Fpn and raises it to the pth power. Okay. Okay, so we know some element of this Galois group of order n. We want to prove that this element generates the whole group. So all we need to do is show that this element has order n. That will tell us exactly what the whole Galois group is. Okay, so let's look at what powers of this Frobenius automorphism does to elements of Fpn. Well, sigma p to the I of alpha is alpha to the p to the I. Why? Because sigma p takes alpha to n, an arbitrary element, to alpha to the p. And if you iterate this automorphism I times, then you're going to take alpha to the p to the alpha to the p to the p, which is alpha to the p squared. And onwards, you're going to get alpha to the p to the I. Since alpha to the p to the n is equal to alpha, right? I showed this above when I showed that Fpn is the splitting field of this particular polynomial where you take alpha to the other side. Since alpha to the p to the n is equal to alpha, we see that sigma, the Frobenius automorphism, the nth iteration of the Frobenius automorphism is the identity in the Galois group, because its action on n arbitrary alpha in the finite field of order p to the n is doing nothing. So the nth iterate of the Frobenius automorphism is the identity element in the Galois group. And finally, the last thing we have to show is that no lower power of the Frobenius automorphism can be the identity. Why is this true? This is true because suppose there was a lower power, which is the identity. So then say sigma p to the I. Then you would have alpha p to the I is equal to alpha for all alpha in the finite field, where I is less than n. So you have this equation, but this is impossible since there are only p to the I roots of this equation, right? There are only, if you move alpha to the other side, you're going to get an irreducible polynomial of degree p to the I, and it's separable, so it has at most p to the I roots. But we know that every single element of fp to the n is a root. So you need to have p to the n roots of this equation, but you have at most p to the I roots of this equation, and I is less than n. So this is a contradiction. So no lower power of the Frobenius automorphism can be the identity. Therefore, the Frobenius automorphism generates a subgroup of order n, and since the group is order n, the Frobenius automorphism generates the whole Galois group. So now we know the entire structure of a finite field. You take a finite field, what is its order? That determines the Galois group. Right. Its order has to be a prime power, p to the n, and there's a unique field of that order. And then the Galois group is going to be cyclic of order n and generated by the Frobenius automorphism. So that's really cool. The next question is, what are the subfields of fp to the n? Right. So I have the answer right here, but maybe you want to think about this. Like, someone tell me, what are the subfields of fp to the n? Like, how would you use this knowledge to get this knowledge? Yeah, so someone said, find fixed field of some sigma to the I. That's exactly it. So the answer is to use the fundamental theorem of Galois theory. So once you know the what the Galois group is, and in this case the Galois group is cyclic of order n, we can use the fundamental theorem of Galois theory to get the lattice of subfields of the extension. And in this case, the Galois group is just z to the n, so the subfields correspond to subgroups of z to the n. Right. What are the subgroups of, not z to the n, I mean z mod n z. So the group, the cyclic group of order n. So what are the subgroups of the cyclic group of order n? For every divisor d of n, you can look at the order bit of sigma to the d in this subgroup, in this group, and that's going to generate a subgroup, sigma to the d. Every divisor of n, sigma to the d, is going to generate a subgroup. Furthermore, the cosets of the subgroup sigma d have, so the z, okay, so you're looking at the cosets of this subgroup, and that's going to be the order of this subfield over fp. Right, remember what we said. You have a field, you have a subfield. K is the field, is the extension of the ground field. Okay, I think I need to just stop using a highlighter. So this is, so you have F is the ground field, K is the extension, and E is some arbitrary sub-extension of K that contains F. The fundamental theorem of Galois theory, one of the parts tells us that the degree of E over F is equal to the coset, is equal to the index, right? That's the word. The index of the Galois group over the subgroup that for which E is the fixed field of, right? So in this case, G is Z mod NZ, so it's has order n, and H is generated by sigma to the D. D is a divisor. So G mod, the index of H and G is, well, what is the order of H? The order of H is N over D, right? How do you get to the identity using this generator? You have to raise sigma to the D to the N over D, and then you'll get sigma to the N, which is the identity, right? So the order of the subgroup is n over d, and therefore the index of the subgroup is just d, right? Which is n over d, right? So the index of the subgroup is d, and therefore the degree of this sub-extension is d. Okay, so I just needed to clarify that. Right. Hold on. Okay, so now that makes sense. And where are we? So for every divisor d of n, there's a unique subfield of degree d over the ground field fp. Right? Why is it unique? Because the subgroups of z mod nz are unique for each order, right? So z mod nz has a unique subgroup for each order of each index that divides n. Okay. So I'm just saying that the subgroups of z mod nz are unique up to order, right? Okay. For each order, there's a unique subgroup of that order. Okay. So for each divisor d of n, there's a unique subfield of degree d over the ground field fp. Namely, it's a fixed field of the subgroup generated by sigma p to the d, the dth iterate of the Frobenius automorphism. And therefore, it's isomorphic to FPD. Remember, we said that finite fields are unique once you specify their order. And the order of this fixed field has to be p to the d because it has degree d over the ground field. So it has to be isomorphic to FPD. And now, so all of this together, everything that we talked about today so far, proves proposition 15, which is the following three statements. So first, any finite field is isomorphic to fp to the n for some prime p and some integer n greater than or equal to 1. The field fp to the n is the splitting field over fp of the polynomial x to the pn, x to the p to the n minus x, with cyclic Galois group of order n generated by the Frobenius automorphism sigma p. Finally, the subfields of fp to the n are all Galois over fp and are in one-to-one correspondence with the divisors d of n. Okay, maybe I didn't talk about this statement, but it's clear because why? Okay, the statement is the subfields of fp to the n are all Galois over fp. We showed that they're isomorphic to fp to the d. Those are the subfields. And for every divisor, you have a unique subfield that's isomorphic to fp to the d. But why are they Galois? Well, first of all, they have to be Galois because these are isomorphic to the splitting field of some irreducible separable polynomial. Second of all, this is an abelian group. So whenever every subgroup is normal, so by the fundamental theorem of Galois theory, this is another way to see it. By the fundamental theorem of Galois theory, since every subgroup is normal, every subfield is a normal extension or a Galois extension over the ground field. And it has subgroup, it has Galois group equal to z mod dz. Right? That is the quotient of sigma p mod this subgroup, this group mod sigma p to the d. Right? It has that quotient group has order d. And it has to be that this subfield is Galois over the ground field, and it has to have Galois group equal to z mod dz because the subfield is subfield is isomorphic to this field, and we already proved that this field is galois with cyclic galois group. So it's all consistent and it makes sense. Okay, back to the statement. The subfields of Fp to the n are all galois over Fp and are in one-to-one correspondence with the divisors d of n. They are the fields F sub p to the d, the fixed fields of the dth iterate of the Frobenius automorphism. Okay, so that's all of this stuff that we've probably already seen. Any questions about this so far? Up to proposition 15. Okay, I think we're good. Now let's move on. So an elementary application. So the rest of this section is gonna be a corollary 16, which I'll prove, and corollary 17, which I'll prove. But then everything after that, I have to look at the book while lecturing. So yeah, I don't have notes written for stuff after corollary 17, but proposition 17, but hopefully we'll figure it out. All right, so an elementary application of proposition 15, the structure of finite fields, let's say. All right, so this application is going to be about the polynomial x to the fourth plus 1 with a polynomial with integer coefficients. So corollary 16. The irreducible polynomial x to the fourth plus 1 is reducible modulo every prime p. Right. So this is kind of weird. Like, okay, how would you normally prove this without Galois theory and stuff? I don't know. How do you prove that an irreducible polynomial with integer coefficients suddenly becomes reducible when you mod all of the coefficients mod p? Right? These like, it's not even that the polynomial changes mod p when you look at it, mod p, the coefficients, because the coefficients are just 1 and 1. And so the polynomial doesn't look different on the surface with mod p coefficients, but you can have a factorization mod p, meaning you can find 2 or more polynomials. When you multiply them together and have mod p coefficients, they're gonna get you x to the fourth plus 1. You can't have this over the integers because this is irreducible over the integers. It has no roots in the integers. It doesn't have any quadratic factors over the integers either. But somehow it becomes reducible modulo every prime p. Okay, so let's try to prove this. So let's consider the polynomial x to the fourth plus 1 over the field. So let's consider it as an element of this polynomial ring with coefficients in fp for the prime p. So saying it's reducible mod p is the same thing as saying it's reducible in this polynomial ring. Okay. Consider the case p equals 2. In this case, x to the fourth plus 1 is equal to x plus 1 to the fourth and is reducible. Why is this true? It's the same reason why the Frobenius automorphism is an automorphism. It's because whenever you take, okay, forget that this is a 4, let's make this a 2, right? So x plus 1 squared is equal to x squared plus 1 squared, which is just 1. So if you just made this a 2, that would be x squared plus 1. And the reason for that is because we're in characteristic 2, right? So doing that kind of thing, like, works. So like raising to the second power is distributive over addition. Like, okay, only because we're in characteristic 2. So if you do that Frobenius automorphism type thing twice, you're gonna get to the fourth power. So in characteristic 2, x plus 1 to the fourth is going to give you x to the fourth plus 1 to the fourth, which is just 1. Okay, so we've shown that in the case p equals 2, this polynomial is reducible. Okay, now the next case and the remaining case is the case when p is odd. Okay, so again, we're trying to prove that x to the fourth plus 1 is reducible mod every prime p. And now let's consider the case where p is odd. Okay, first of all, p squared minus 1 is divisible by 8. Why is this? Well, since p is odd, you know that p mod 8 is either 1, 3, 5, or 7. These are the only odd numbers mod 7. So p squared is equal to 1 mod 8. Why? 1 squared is 1 mod 8. 3 squared is 9, which is 1 mod 8. 5 squared is 25, which is 1 mod 8, because 25 is 24 plus 1. 7 squared is 49, which is 48 plus 1, which is 1 mod 8, because 48 is 8 times 6. Yeah. Yeah. So we've just shown that p squared for any odd number, not even the fact that it's prime, we're just using the fact that it's an odd number, p squared is equal to 1 mod 8. And therefore, p squared minus 1 is equal to 0 mod 8. So p squared minus 1 is divisible by 8. Okay. All right. Now, since 8 divides p to the p squared minus 1, we know that this polynomial, x to the 8 minus 1, divides x to the p squared minus 1 minus 1. Why is this true? This is true because any root of this polynomial is an eighth root of unity, right? And any root of this polynomial is the p squared minus 1th root of unity, right? So if you have an eighth root of unity, you're also a p squared minus 1th root of unity, because 8 goes into p squared minus 1, right? If you take a eighth root of unity and raise it to the p squared minus 1, you're going to raise it to the 8 multiple times. And each time you raise it to the 8, you're going to come back to 1. So if you're raising it to a multiple of 8, it's still going to be 1. Another way to think about it is you're taking a root of this guy, so an eighth root of unity, you're raising it to the 8th power, and then raising it to the other factor of this guy. So p squared minus 1 is equal to 8k. So first you're raising this root to the 8 and then to the k, which would give you p squared minus 1. So you're raising it to the p squared minus 1. But once you raise alpha to the 8, you have 1, and then to the k is going to still give you 1. So any eighth root of unity is a p squared minus 1th root of unity. So any root of this polynomial is a root of this polynomial. And since both of them are separable polynomials, all of the roots of this guy are roots of that guy, and therefore this whole polynomial is divides this guy. Another way to see it is you could factor this guy in its splitting field into a bunch of linear terms, linear factors, and all of the linear factors that multiply to give you this appear in that list of linear factors over here. And when you multiply those linear factors together, you get x to the 8 minus 1. And those linear factors, which are not the ones that divide this guy, give you the other thing. So you can write this as a product of this and some other polynomial. So x to the 8th minus 1 divides x to the p squared minus 1 minus 1. Okay. Now we have this chain of divisibility. So first of all, x to the 4th plus 1 divides x to the 8th minus 1. Why is this? Well, no. First of all, notice that x to the 4th plus 1 is the polynomial that we even care about. Like, that's the whole goal of this thing. So we're going to show that this guy is divisible all the way to this guy. But first of all, why is x to the 4th plus 1 a factor of x to the 8th minus 1? Well, this is because of that difference of squares thing. So what is x to the 8th anyway? X to the 8 is x to the 4th squared. So x to the 8 is a square, right? And so x to the 8 minus 1 is a difference of squares. So you have x to the 8 minus 1 can be factored as x to the 4th plus 1 times x to the 4th minus 1, like using the difference of squares property. So this guy is a factor of this guy. Next, this guy is a factor of this guy, as we just shown. Next, this guy is a factor of this guy. You multiply this guy by x, right? So x to the p squared minus 1 all times x is going to give you x to the p squared minus x. So all the roots of x to the 4th plus 1 are roots of x to the p squared minus x. That's what it means for this guy to be a factor of this guy. All right. Now, what's the punch? The punchline is that since the roots of x to the p squared minus x form fp squared, a finite field of degree p squared, of order p squared, a degree 2 extension of fp. So this sentence right here is how we're using the knowledge that we gathered to prove proposition 15. And that's why this is a corollary of 15. All right. Since the roots of x to the p squared minus x form this finite field, and which has degree 2 over the base field fp, it follows that all of the roots of x to the 4th plus 1 generate an extension of degree at most 2 over fp. Right? We showed that x to the 4th plus 1, all of the roots of that guy are roots of this guy, which is the separable polynomial, whose splitting field gives you the finite field of order p squared. So x to the 4th plus 1 cannot be irreducible over fp, since adjoining a root would produce a degree 4 extension over fp. So this is a contradiction. Before I talk about the contradiction, let me just go back to this. The roots of x to the 4th plus 1 generate an extension of degree at most 2 over fp. The reason for this is because the roots are contained in this degree 2 extension. So the roots of x to the 4th plus 1 can only generate a field that's contained in fp squared. So the roots can only generate an extension of degree at most 2, because it has to be a subfield of fp squared. Now, okay, what would happen if x to the 4th plus 1 were irreducible over fp? Then adjoining a single root of x to the 4th plus 1 would give you a degree 4 extension over fp, because if you adjoin a root of an irreducible polynomial, you should get an extension of the degree equal to the degree of the irreducible polynomial. So this is I think the first main theorem that we proved in this whole course. Like, degree of a simple extension obtained by adjoining a root of an irreducible polynomial is the degree of the extension. The degree of the extension is the degree of the irreducible polynomial. So in this case, it has to be 4 because the degree of this irreducible polynomial, okay, it's not, if it were irreducible, then the degree of this irreducible polynomial, the degree of the extension would have to be the degree of this irreducible polynomial, which is 4. But we just showed that it has to be, if you would join all of the roots, not even just one, all of the roots, you would get a degree at most 2. So this guy cannot be irreducible. So that's the contradiction. All right. Any questions about this whole argument? It's a pretty cool argument. Yeah. Okay. That we used galois theory or like this whole thing about finite fields to show that x to the 4th plus 1 is reducible mod every prime. Okay, the last thing I'll finish off, since we're so close to the hour, and I started late anyway, and I have to go after this soon. I'll just finish off with proposition 17, and we'll finish the rest of finite fields on Friday, and maybe cover more stuff on Friday too. So this is the last thing I want to say. So first, this note: the multiplicative group of the finite field is cyclic. Okay, this is some background knowledge. To be honest, when I took Galois theory, this was not. I didn't. If I did learn this before, I didn't remember why it's true. So if you have a finite multiplicative group, if you have a finite subgroup of the multiplicative group of a field, it has to be cyclic. That's a general statement about group theory, right? Or field theory, right? If you take any finite subgroup of the multiplicative group of a field, it has to be cyclic. Like think about C. This is a field, right? And then look at its multiplicative field and look at its finite subgroups. What are the finite subgroups of the multiplicative group in C? So these are the elements of C that have finite order. So they're elements alpha in C such that alpha to the n is equal to 1 for some finite number n. So these are roots of unity. And we know that the roots of unity are cyclic. Like a finite subgroup of roots of unity is cyclic because you can find the one with the smallest, you can find one that generates all of the other ones in the subgroup. And yeah, it's cyclic because it goes in a cycle. Right? So that's the intuition with C, but in general, in any field, in this case, our field is FPN. In any field, if you take a finite subgroup of the multiplicative group of that field, you're going to get a cyclic group. And this requires proof, but I'm not going to prove it. Okay. In particular, just the plain multiplicative group of a finite field is a finite multiplicative subgroup of the multiplicative group because it's finite to begin with. So this has to be cyclic. Okay, so we're invoking some group theory / field theory knowledge here, which we're not going to prove, but you should look up the proof if this is not clear, if this is not known to you, or it wasn't known to me when I took the course, but yeah. Okay. So let's prove. So what does this imply? This implies that there's a generator of this multiplicative subgroup, multiplicative group of a finite field. There has to be a generator which generates a cyclic group, right? So that's what it means to be cyclic. So phi is a generator of the multiplicative group sigma p to the n, right? Since phi is a generator of this group, we know that you can like then obviously like this field fp to the n is a simple extension where you just extend the base field by joining this element phi, right? Because phi itself, powers of phi give you everything in FPN besides 0, and 0 is in the ground field. So everything in here is covered by this simple extension. Right. So we just proved proposition 17. The finite field Fp to the n, the unique field of order p to the n, is simple. In particular, there exists an irreducible polynomial of degree n over Fp for every n greater than or equal to 1. So why is this statement true? Well, first of all, why is this statement true? This is just this thing. It's a simple extension where you adjoin the a single generator of the multiplicative group. So this is a simple field, simple extension of the ground field. And why do there exist irreducible polynomials of degree n over Fp? Because if this is a simple extension, then what this is an extension of the ground field Fp by a root of an irreducible polynomial. It's the extension of Fp by an irreducible by a root of an irreducible polynomial. So this has to be the root of an irreducible polynomial. What is the monic? What is it called? The minimal polynomial of phi. That minimal polynomial gives you is the irreducible polynomial of degree n over Fp. So since for any n greater than or equal to 1, you can write this as a simple extension, there exists irreducible polynomials of degree n over Fp for every n greater than or equal to 1. Okay, and we're going to use this on Friday to prove some more things about polynomials and stuff. But yeah, that's all.